Dr. Masson, can I ask a question before we get started?
You may.
About the homework problem. I commented on the one that's for plug and mixed flow models under ESPs. I'm still kind of confused with are we comparing gravity settlers and centrifugal separators, or is it?
What I'm really asking for isn't so much what you're comparing as far as the process, but what is the difference between plug flow and mixed flow? So when we talk about plug flow, what does that mean? Okay, so in terms of looking at longitudinal dispersion, vertical dispersion, how gases are flowing, and the question's really irrelevant to the reactor itself, but to the process.
Okay, that makes sense. Thank you. And for the economics part of the problem, that's regarding ESPs, correct?
Correct.
Okay, thank you so much.
I just basically want you to have some understanding of what that means in terms of, if you've got a BIMX flow, what does that mean in terms of efficiency versus a plug flow? And how does that translate, for instance, to the size of the unit? What does that mean in terms of capital costs, operating costs, et cetera?
Okay, thank you.
Okay, no problem. That's why I like doing things online, live, because we can address issues like that. Okay, just want to make sure I am recording. Couple reminders in terms of work that's due. The particulate removal homework on filtration devices and scrubbers is due next Wednesday. So there's homework due tonight. I should have left that on there because today's the 8th. So you've got homework due tonight on gravity settlers, centrifugal separators, and ESPs. So that's due at 11:59. I made the homework on filtration devices and scrubbers due on Wednesday because of both Easter and Passover. So hopefully that works for everybody. If it's a problem with the holidays, let me know and we can adjust those dates. The date for the 15th. And then just a reminder, the participation question is open on Friday. And I think what I'll do is I'll just leave that open instead of through Sunday. I'll leave that open through Monday for those of you that are celebrating both Passover and Easter this weekend. Does that make sense for everybody, or that work for those of you that are on? Yes, no?
That works.
Okay, thank you. Okay, so continuing on, looking at air filtration on Monday, I had added that extra lecture looking at face masks. Again, that was not a lecture that I had done before, but I thought it was very relevant to the situation we're living in right now. So what I'd like to do today is we'll move back, look back at industrial processes. So we'll really focus predominantly on what are referred to as baghouse filters. So this is really what we'll focus on, although recognizing that essentially the same process is what's used in a number of types of surface filters. And talked briefly about this on Monday in terms of the types of materials that are used. Be sure to watch the video because there's a nice animation in there about the different mechanisms by which particles are removed in filters. It's better than what I can draw by hand. It's kind of a neat animation that's there. So take a look at that. We'll talk a little bit about mechanisms, but it's really worth watching that video, and embedded in the PowerPoint is the link if you want to watch the whole video. So as I mentioned on Monday, these filters can be made with a variety of different types of materials. We'll focus this time on basically, again, on fabric filters, but we'll look at it more from the aspect of what are we removing in an industrial setting. When we talk about filters, we can talk about high efficiency particulate air filters. Now, these are filters that are used, for instance, in a air conditioning system, furnace. Many furnaces, in fact, most furnaces have some sort of a air filter on those. Cars even have air filters on there. These, in a home setting, these are what are referred to as HEPA filters. These are high efficiency particulate filters. So the focus here, actually here, is on the 0.1 micron size particle. We had talked about mass, so it's really tested to remove 0.3 microns, but here HEPA filters are actually tested to remove 99.9% of the 0.1 particles. And then we can have ultra high efficiency particles. These are more likely to be used in a laboratory, in a hospital, where it's critically important to remove these particles, especially when you're talking about viruses. And these have a much higher efficiency. They also have a much higher pressure drop across the filters, but they do remove, in this case, what would refer to as 6-9 removal of a 0.1 micron size particle. These can also be used for removal of toxic particles. They can be used for removal of radioactive materials. And then, as mentioned, microorganisms. In particular, you're looking here at removal of viruses, although bacteria would also be removed. Now, in an industrial system, we're not going to achieve removal efficiencies as great as what we just mentioned with a HEPA or an EUPA, ultra high efficiency system, but we do achieve very good efficiency, typically 99 to 99.99, so what would we refer to as 2.9 to a 4.9 log removal. And this is typically with about a 0.5 micron size particle. They can remove particles down to 0.01 microns, and we'll talk more about that when we look at the mechanisms. Dust loadings, highly variable, from relatively low dust loadings of 0.2 grams per cubic meter up to 23 grams per cubic meter. So to give you an idea, when we talk about particulates in the atmosphere, we're talking about milligrams or micrograms per cubic meter. So you're talking about quite high dust loadings. Now, variety of materials can be used, and notice that there's significant temperature differences here. So for instance, if you're looking at cotton polypropylene, you're looking at temperatures less than 100 degrees C. If we need to treat a gas stream at temperatures greater than that, so between 100 to about 250 degrees C, then we're looking at some polyester, some Teflon, very specific proprietary materials. And then we can go even higher to 260. And now we're looking at polyamides or fiberglass. We can actually go even higher. We can actually go up to about 980 degrees C. And now there we're looking at ceramic filters. So the temperature, as temperature increases, the cost also increases. Your cost of your materials will increase significantly. Now, how do we pick the type of material? Well, one, it's going to depend on the type of collector. So versus a HEPA filter for a home, you're typically off looking at fiberglass. For a industrial environment with a baghouse filter, which is the type of units that we're often talking about, there it really depends on the type of baghouse filter. So it's kind of an operational mode. We'll look at that. It'll depend on the cost. How affordable is this material? And then it's going to depend very much on your operating temperature, the physical chemical characteristics of your particles and your gas. So how corrosive is that gas? How abrasive are those particles? How combustible are those particles? If you've got combustible particles, you want to make sure you're using materials that aren't highly flammable. So you're less likely, you don't want to be using cotton or a polyester material if you have a highly flammable gas. The other issue really is temperature. So one of the problems is if we have a lower temperature, so less than 100 degrees C, we can get condensation on your filter. You're going to have water. Now remember, kind of think back at what we've talked about, for instance, with acid rain. You have SO2, you have water. What do you produce? Sulfuric acid. We have NOx, we have water. Potentially, what can we produce? Nitric acid. So the problem is that if we have water, we have the potential for corrosion, and then degradation of your filter. And as we talked about with masks, and this was mentioned in that video that I showed, if you have a leak, that's where air is going to flow. It's going to flow through the path of least resistance. So if there is some sort of a tear or damage to a point, particular point in this filter, air is going to flow preferentially through that. It's going to leak. You're not going to get as good removal. Now, if we operate at lower temperature, then we need less pre-cooling. Because often the gases are from a combustion process. If they are, then they're hot. So in which case you've got to cool these gases before you put them through the filter. If you can operate, if you can operate at high temperature, we don't need to cool that gas. But then we have to be careful. Higher temperatures, higher likelihood of an explosion or a fire. So it's essentially those two issues in terms of the lower temperature condensation, higher temperature, less pre-cooling. Those aspects are played off against one another to try and decide what the operating temperature is. Now, some of the advantages of these industrial surface fabric filters, or what are referred to as baghouse filters, they have a high collection efficiency. As was mentioned, we're looking at potentially greater than 99.99%. Okay, they're extremely flexible. Remember with the ESPs, when we talked about those are not flexible at all. So once they're designed for a particular flow rate, they're designed even for a particular particle characteristics. And if we, for instance, change the fuel, that's going to change the characteristics of those particles, and you're going to see significant differences in the efficiency of the ESP. These baghouse filters are essentially more forgiving. You're going to see less changes in efficiency. So they're extremely flexible. You can operate these at a wide range of flow rates. And that allows you to change your operation, shut down a baghouse filter if you need to, and operate just with the others. They also have a reasonable pressure drop and power requirements, so that makes them ideal for these industrial settings, and they can handle a variety of materials. The biggest disadvantage is the space. They're large. Similar, the ESPs are also large, but these are large devices. They take up a lot of space. And another disadvantage is because these units, the collection device is actually made out of fabric in many cases, there is the possibility of explosions or fires. And then the other issue is they can't treat hygroscopic materials. So they can't treat materials that are very gelatinous, that absorb water, because it's very, very difficult to remove that material from the actual filter. I'm not going to talk extensively about the mechanisms. I encourage you to go back and look, if you haven't watched it, the Monday's lecture, and embedded in that is that video on how masks work. But it really talks about, for instance, issues of diffusion. So Brownian motion, those really, really small particles that interact with your filter material and are removed by diffusion. And then it talks about those larger particles that are removed by inertial impact. These particles are too large to actually remain with the flow path. They deviate from the flow path, and essentially they kind of crash into a filter material. And then they talked about sieving. So these are the really, really large particles that essentially, for instance, if we think of our filter material, it's kind of a woven material like this. So basically, when we're talking about sieving, we're talking about, for instance, these large particles that are actually blocked from moving through the filter itself. So here, we're talking about sieving. So inertial impact, they're really the big particles. They're not as big as those that are removed by sieving, but they deviate from the flow path. The really small particles that are removed by diffusion. And then we have interception. These are particles that move through, they're able to fit through your spaces, the pores of your material, but they stay with the flow path, but they come in contact with that filter material and they adhere to the filter material. And then the electrostatic attractions, this is what we're looking at when we're really talking about how the particles adhere to and stick to that filter material. So there has to be some sort of an attraction force. Otherwise, those particles would just detach from that material and move right through. So we have both a removal mechanism, but we also have to have some sort of an attraction to keep those particles on the filter. Now, when we talk about efficiency, here, number of things we need to think about. One is the efficiency increases with time. And the reason that happens is kind of thinking back, okay, here's our filter material. Change colors. Okay, so we have what happens, okay? So basically, we've got these particles that are getting stuck in the filter. And some are really large and they stick on the outside. So basically, essentially, you can kind of think of it as almost a coating. So over time, you're going to get particles sticking. They decrease the pore space. So you see a decrease in pore space, and you see what's referred to as a filter cake. So you can think of having done a filtration in the lab. You do a filtration in the lab, you're filtering in this, typically you're filtering water, but the same is true with air. And what over time, okay, as you're filtering, you get particles depositing, you can see it on that filter. And then over time, the flow rate decreases because the pressure drop decreases, or pressure drop increases. So you get this what we call a filter cake forming. Porosity decreases, pressure drop increases. And actually your efficiency actually increases with time, because now what happens is as those pores decrease in size, it's harder for those particles to get through that filter. We describe the efficiency as the mass of particles collected divided by the mass we applied. Okay, and the difference is what goes through that filter. So the mass collected is just M, so that's the mass. And the efficiency is better color here. The efficiency is your particle loading, so your concentration. Q is your flow rate, and T is the operational time. Okay. So this gives us the mass of material that's actually applied to the filter. The filtration velocity is also known as the air to cloth ratio, and that ranges from about 0.01 up to about 0.2 meters cubed. So it's meters cubed per second, so it's flow rate divided by meters squared, and that meters squared is the surface area of your filters. So in this case, the meter squared is the surface area of the filter. And it's actually the filter bags. Okay, think about that in vacuum cleaner. You've got a vacuum cleaner bag. It would be the surface area, the inside surface area of that vacuum cleaner bag that you were using to clean your apartment or home. V sub S here is the approach velocity. And this here is, sorry, V sub S. So it's your approach velocity, also, like as I mentioned, also referred to as the air to cloth ratio. The efficiency depends on the integrity of your material. If you start having pinholes in this material, you're going to have preferential flow through those pinholes, and you're going to see significant reduced efficiency. So this is a table from the FE reference handbook. It is air to cloth ratios, and notice that they vary both with the material that you're removing. So for instance, if we're looking at a cement processing facility, we're typically looking there at removal efficiencies with what we refer to as a reverse air unit of about 0.6 meters per minute, with a pulse jet. And we'll talk about these. They're just different types of baghouse filters, much higher at 2.4. On the other hand, if you're looking at removing fly ash, so you're in a power, looking at a baghouse for a power plant, it's about 0.8 for reverse air and about 1.5 for a pulse jet. So they do vary quite a bit depending on both the material and on the type of unit that is being employed. The other property that we typically use with filters is permeability. You've heard of permeability referred to, I'm sure, if you took ENE 421 hydrology. We talk about permeability of soils. We also talk about permeability of fabric materials. So you can think about this as the ease by which the fluid moves through the material. It is a function of the filter media. It also changes over time. So as this filter cake, and you can see it here, as this filter cake builds up, your permeability decreases. It's a function, so it's a function of the thickness. And that thickness is going to change over time. And it's a function of the head loss, so the pressure drop across this filter. These are just two images of, I'm just going to expand this a little bit. Two images of baghouse filters. So what you have, and you can see it here, this is actually, the one is a reverse air cleaning unit, but you have airflow, you have a dust collection device, and you're removing air, you're removing those particles over a period of time, okay? And then periodically, just as if you have a vacuum cleaner, you can't keep the bag in there forever. At some point, you have to shut down the vacuum cleaner. You either change the bag, or if you have a system where you can remove the bag and you deposit the dust that's been collected into the garbage. Well, it's essentially kind of the same thing. It's just more automated than what you would do with a vacuum cleaner bag. These bags here, they show, it's easier to see it here. So these bags here can be up to about 40 feet long. So they're much, much larger than what you would have in your vacuum cleaner. They can be up to about, this is not one right. They can be up to about 5 to 14 inches in diameter. So this is for each bag. Okay, so just think about that vacuum cleaner bag. Okay, think about how big that vacuum cleaner bag is that you have in a household vacuum cleaner. These would be up to 40 feet long and up to about a little more than a foot in diameter. One large baghouse can actually remove, this is one large baghouse filter can remove up to 6 tons of particulate matter per hour. To give you a sense of the size, this is a baghouse filter used in a large automotive foundry. There is 16 compartments, 4,000 bags. Each bag is 22 feet long and about 7.5 inches in diameter. So there's 4,000 of those that have to be maintained. You can imagine the size of the footprint for such a large unit. So let's look at an example. This is actually for an actual power plant. And it had one of the first baghouse filters that were constructed and operated. It was a coal-fired power plant. And because it was one of the first, there was extensive testing done on this unit. So this unit has six compartments. Each has 112 bags, and each bag is 8 inches in diameter and 22 feet long. There is an active filtration area of 46 square feet per bag, and the gas being cleaned has a flow rate of 86,240 cubic feet per minute. The pressure drop through a freshly cleaned filter is 0.5 inches of water, and the bags are operated until the pressure drop is 3 inches of water. One of the things to think about and it's really true with essentially all filtration devices, you either operate at constant pressure or you operate at constant flow. So in this case, the pressure is changing during the operation, so it's operating at constant flow rate, increasing pressure. You can't keep both of them constant. One is going to change. So in this case, pressure is increasing, flow rate stays constant. We're going to clean once per hour, and the incoming gas has a particle loading of 13 grains per cubic foot and a collection efficiency of 99%. The filter cake is 50% solids. And just this grains, a grain is, so 1 grain is equal to 65 milligrams. 16 grains is equal to 1 gram. 440 grains is equal to 1 ounce. Give you a conversion there from grains. So let's look at this problem, and I'm going to add in a new slide. So what do we have? We have a situation, we've got 112 bags, 8 inches in diameter, 22 feet in length, and a area equal to 46 feet squared per bag. you're told you have 6 compartments. But we're going to assume that at any point in time we have 1 out of service. So we have 5 compartments in service at any time. And we have a flow rate equal to 86,240 cubic feet per minute. We need to calculate that superficial velocity, or the air to cloth ratio, also referred to as a face velocity, and that is equal to 86,240 cubic feet per minute divided by 5 times 112 bags times 46 feet squared per bag. So this is the 5 units. This is how many bags we have per unit, and the area per bag, and that is equal to 3.35 feet per minute, which is 1.02 meters per minute. The actual, what we refer to as the interstitial velocity, is actually significantly greater because we have the pore space is 50%. So the velocity, the actual, if we were to measure a gas parcel, the actual velocity of the gas parcel would be greater than what we just calculated. M over A, so the mass over the area is equal to our dust loading times this superficial velocity times the efficiency times the time of operation. So our gas loading is 13 grams per cubic feet. There are 7,000, sorry, I said grams, grains, 13 grains per cubic foot. There are 7,000 grains per pound. Our velocity is 3.3 feet per minute. We have 60 minutes per hour. The efficiency is 0.99, so we said it was 99% efficient, and we're operating for 1 hour. And if we multiply that, that is 0.37 pound mass per feet squared, which is equal to 1.8, and it's kilograms per meter squared, and that's of your fabric. So that's of the filtration area. So let's assume a density of 2,000 kilograms per meter cubed for the particles. This is for our particles. We have 50% porosity of that material. So the actual density is, so that's when those particles deposit, we're assuming that there's 50% porosity. So this is of the filter cake. So that's the density of the filter cake. So this is going to be 1,000 kilograms per meter cubed. And we have 1.8, and I'm switching to metric. As you all know, I much prefer metric. And if we divide this by the density, and that is 1.80 times 10 to the minus 3 meters. What we just calculated right here is the thickness. And that is 0.071 inches. So basically what we've calculated here is the thickness. We first calculated the mass per area. So this is M over A. What we then calculated was the thickness. So by taking that value and dividing it by the density, we can calculate the thickness of that filter cake. And we see that that filter cake is about 1.8 millimeters in thickness, or about 0.071 inches. We have some more space. Let's just add another slide. You were also asked for the permeability, and rearranging the equation that we, actually, if we look back, so here we have the equation for the permeability, so we don't have to rearrange that. Okay, so our permeability is equal to V sub S delta X, our thickness, over the viscosity of the gas divided by the pressure, and that's a pressure drop. So permeability actually becomes positive. So we have 3.35 feet per minute. .071 inches divided by 12 inches per foot. So that was delta X times the viscosity times 2.09 times 10 to the minus 5. This is just a conversion, pound force second over pound squared CP. And now we will divide all of that by the pressure drop. And this is a negative, it's a pressure drop, so it's negative inches of water. And we're just converting pound force per pound per foot squared, inches of water. And that gives us 7.96 times 10 to the minus 12 feet squared. So that is K. So that's our permeability. So typically you're going to see permeabilities that are extremely small. Much smaller than, for instance, what you would see even in a groundwater system. The life of these baghouse filters typically ranges from about 1 to 5 years. Actually, average is about 2 years. So basically, think about that example where, back here, okay, you've got 6 compartments, each with 112 bags. Every one of those bags has to be removed about every 2 years and replaced. Talked about bag lengths and diameters. Where we talk about cages, you can kind of see here the bag, how the bag fits over this caged mechanism, and it keeps that bag much more rigid, where in this case you can see there's kind of a ring here, and these bags are much more flexible. So these are much more rigid, and these are going to be much more flexible. And so you see some differences there. And lastly, we mentioned we have some basically 3 different types of units. We have a reverse air. So basically this here, if we think, here's our bag. And this is an inside out. So we're operating where the dirty air goes on the inside. The particles are collecting on the inside of that bag, and the clean air comes on the outside. So like most vacuum filters, okay? The clean air comes on the outside of that bag. What's collected on the inside is the dust. And then when we want to clean these filters, we typically take them offline. So we stop the flow, and then air is reversed. So during the cleaning mechanism, switch colors. So during the cleaning, now do we have clean air here? Our particulates flow out the bottom, and they're collected typically for disposal. And as I said, generally, the unit is taken offline. So for instance, in the previous, you had 6 compartments. One, when it's cleaned, 1 compartment is taken offline, it's cleaned, and then the air flows through the other 5 compartments. We have a pulsed jet, and these are framed. So these are the more rigid structure. So you have a frame and the bag built over this frame or cage. Here, the particulates collect on the outside. So here's the bag. So the particulates are going to collect. So here's our dirty air. The particulates collect on the outside, and the clean air flows through the center. So this is actually referred to as an outside in mode. The previous was an inside out. And here, these are actually the way that these operate typically is the unit uses compressed air. So that's why there's pulse jet. So it's using compressed air to remove this material that's collected on the outside. And this can be operated either with an offline mode. So you take the compartment offline, pulse jets of air to clean the bag, or they can actually be operated with a continuous online mode and a fully automated system. The last type is a shaker. Again, these use these more rigid cage structures, and the air can flow either inside out or outside in. And basically, this is a mechanical shaking device. So when you've achieved a maximum pressure, the system would be shut down. These get shaken. So basically, they just get shaken, and the particles fall out. This is actually one of the most common types of baghouse filters, is the shaker operation. And just some final thoughts about baghouse filters. When we're looking at these baghouse filters, the filter bags are actually not the medium that's doing the majority of the filtering. It's actually the filter cake. So that filter cake that builds up, that's what's actually going to be much more efficient at filtering than the filter itself. So you'll actually see a increased efficiency over your operational time. The baghouse, the life of that baghouse is predominantly affected by the cleaning frequency and the energy by which you have to clean it. The harder to remove that material, the more energy you need to use to detach that material, and the more often you're going to have to change those filter bags. And overcleaning is worse than undercleaning. under cleaning, you're gonna reach that maximum pressure quicker, but you're not going to deteriorate the integrity of the bags as quickly as you would if you over clean. So we will end there. And if you have any questions, I'm happy to take this. Otherwise, I will see you on Friday.
Hello, Professor.
Yes.
I have a questions from the homework class here or in the office hour.
Mm-hmm.
The question is cyclone separator questions B. I don't know why I'm